Welcome back, everybody, for another deep dive.
Yes.
This time, we're going to explore something called P-Adic numbers.
Yeah. Okay.
And you've given me a mix of some academic papers and even a YouTube video from Eric Rowland.
Right.
So I'm really curious to see where this goes.
Yeah.
Apparently, these P-Adic numbers, they completely change how we think about size and distance.
They do.
Even infinity.
Yes.
And I'm ready to have my mind stretched a little bit. Are you?
I think so. I'm very excited about this topic because it really is one of those things that kind of turns math on its head.
Okay.
It challenges like some of our basic assumptions about how numbers work.
So where do we even begin with something like this?
Well, I think the YouTube video is a great place to start.
Okay.
Roland does a really interesting thing where he uses powers of 2 as kind of a visual aid to get us into this idea.
Okay.
And he shows how, like, if you take 2 to the 10th power, 2 to the 100th power, and so on, the digits of these powers start to converge, but not in the way we'd normally expect.
So they're not, like, just getting bigger.
Right. It's not that the numbers themselves are getting closer.
Right.
But their last digits start to stabilize as the powers get higher and higher.
Yeah.
It's a very subtle pattern.
Yeah.
But it hints at this deeper concept called the P-Adic absolute value.
The P-Adic what now?
Absolute value.
Okay.
Yeah.
So it's like a new way of measuring.
Yeah. It's a new way of measuring the size of a number.
Okay.
And this is where things get really interesting.
Okay.
In the P-Adic world, a number's size isn't about how many digits it has.
Right.
But about how divisible it is by a certain prime number, which we denote as P.
Okay, wait. So a big number, like a billion, could actually be small in this P-Adic system.
Exactly.
Okay.
So imagine you're looking at the 10-adic world, right?
Mm-hmm.
A billion is divisible by 10.
Right.
By 100 by 1,000.
Yeah.
So in the 10-adic world, a billion is actually considered quite small.
Really?
Because it's so divisible by 10.
Okay. So that is definitely different than how we normally think about size.
It is.
So how does this P-Adic absolute value lead to these P-Adic numbers then?
Well, think about it like this.
Okay.
In our normal number system, we extend integers to the right.
Okay.
By adding decimal places,
Right.
we get fractions and decimals and so on.
Right.
In the P-Adic world, we extend to the left.
Okay.
With digits based on powers of our prime P.
Okay.
And the more divisible a number is by P, the further to the left its most significant digits extend.
Interesting.
And this is how you get P-Adic integers.
So instead of a decimal point going to the right, we have like a P-Adic point going to the left.
That's a great way to think about it.
Okay.
And we can actually do arithmetic with these P-Adic integers, addition, multiplication.
Wow.
All kinds of interesting things.
So this is twisting my brain a little bit.
Good.
So if these numbers extend infinitely to the left,
Yeah.
does that mean that infinity works differently in the P-Adic world too?
That's a great question, and it really gets at the heart of why P-Adic numbers are so fascinating.
Okay.
They force us to kind of reconsider our assumptions about infinity and how numbers behave.
Okay.
But before we dive into that, I think it's worth talking about why mathematicians usually focus on P-Adic numbers, where P is a prime number.
Yeah, he showed in that video that trying to do division with base 10
Yes.
led to some weird contradictions.
Absolutely.
Right.
Yeah. It's like we're using the wrong foundation for building our P-Adic house.
Yeah, like we're trying to build a house on sand instead of on rock or concrete.
Exactly.
Okay.
And that's why mathematicians focus on P-Adic numbers where P is prime.
Okay.
Because it ensures that we have a consistent and well-behaved system.
Gotcha.
Yeah.
So we've got this strange new way of measuring size.
Yes.
We've got numbers extending infinitely to the left.
Mm-hmm.
We've got prime numbers playing this crucial role.
Yeah.
I'm starting to get a glimpse of what this P-Adic world looks like.
Good.
But it's
definitely different.
yeah, it feels different.
It is.
It feels alien almost.
Yes. So,
And that's just the beginning.
okay.
We've barely scratched the surface here.
Okay.
Those academic papers you mentioned,
Yeah.
they dive even deeper into this world of P-Adic numbers.
Okay.
They reveal connections to areas you might not expect, like string theory
Yeah.
and even the human brain.
Whoa, hold on.
Yeah.
Numbers connecting to the fabric of the universe and how we think.
It's pretty wild.
That's where I start to get really curious.
Yeah.
So what's next in our P-Adic journey?
Well, I think we should move on to those academic papers now.
Okay.
They can be a little dense,
Right.
but I'm here to guide us through and extract those little gems of insight.
I'm all ears, lead the way.
All right, let's do it.
Okay, so last time we went down this rabbit hole of P-Adic arithmetic,
Yeah.
where size is all about divisibility by a prime number and numbers can stretch infinitely to the left.
Right.
We even touched on those hints about connections to string theory
Yeah.
and the Riemann zeta function.
Yeah. It's a lot to wrap my head around.
It is.
But I'm definitely hooked, so.
Good. I'm glad to hear it.
Yeah. Where do we go from here?
Well, those mathematical and physical connections are just the beginning.
Okay.
Now we're going to explore how P-Adic numbers pop up in some truly unexpected places.
Like, give me an example.
So one of the papers on P-Adic mathematical physics talks about using them to model something called spin glasses.
Spin glasses. Okay, that rings a bell, but remind me, they have something to do with magnetism, right?
Yes, exactly. So imagine a material where the atoms have these tiny magnetic spins.
Okay.
Little arrows pointing in random directions.
Okay.
And these spins interact with each other.
Okay.
But in a really complex and disorganized way.
So messy.
It's very messy, like trying to herd cats.
Okay.
Yeah. And that's where P-Adic numbers come in.
Okay.
Remember how we talked about P-Adic distance, where closeness is all about divisibility by our prime P?
Right. It's like a whole new way of measuring distance on a map.
It is. And it turns out that that unique way of measuring distance is perfect for capturing the complex hierarchical structure of these spin glasses.
So the P-Adic distance can represent the relationships between these randomly oriented spins.
Exactly.
How does that even work?
So in a spin glass, you have groups of spins that are strongly connected to each other.
Okay.
And then those groups are connected to other groups, forming this kind of hierarchy.
I see the hierarchy, but how do the P-Adic numbers fit into that?
Right. So the P-Adic distance reflects this hierarchical arrangement.
Okay.
So spins that are highly divisible by the same power of P-A are considered closer in the P-Adic sense.
Okay.
And this closeness can represent their stronger interactions within the spin glass.
So it's not about physical distance.
It's not about physical distance. It's about mathematical closeness.
That's really clever.
Yeah.
But honestly, it's still a little surprising to me that something as abstract as P-Adic numbers can be used to model something as messy and physical as a spin glass.
It is surprising, and it highlights how these numbers transcend different fields of knowledge.
Okay.
But hold on tight because it gets even wilder.
Okay.
This same paper also discusses using P-Adic numbers to model the human brain.
Wait, with the human brain? Seriously?
I know, it seems like a giant leap from spin glasses.
It does.
Yeah.
How can numbers possibly describe something as complex as consciousness and thought?
Yeah, it's a bold idea for sure, and it's still an area of active research.
Okay.
But the basic concept is that the hierarchical structure of P-Adic numbers might be able to represent the way our brains organize information.
Okay, I can see the hierarchical part. Our brains have neurons connecting to form groups, and those groups connect to larger regions and so on.
Exactly like a tree with branches and sub-branches.
Yeah.
Just like with the spin glasses,
Yeah.
the P-Adic distance could represent the relationships between different levels of this hierarchy in the brain.
So are you saying that the way we think, make decisions, even experience emotions, could be described using the same mathematical framework as the interactions of spins in this messy material?
It's a fascinating possibility, right?
Yeah, it is.
It suggests that there's a deep underlying structure to how complex systems organize themselves, whether they're physical or biological.
So P-Adic numbers could be like the key to understanding that.
It's possible.
That's amazing.
Yeah.
But it sounds like this is still very much a theoretical idea.
It is.
Is there any practical application yet for P-Adic numbers in neuroscience?
Well, it's early days, but there are some intriguing possibilities.
Okay.
For example, P-Adic analysis could be used to develop new algorithms for analyzing brain imaging data.
Yeah.
It could even lead to new types of artificial intelligence.
Oh, wow.
Based on these hierarchical principles of P-Adic systems.
So P-Adic numbers might not just help us understand the brain. They could actually lead to advancements in AI, too.
That's the exciting potential.
Wow. Okay. So P-Adic numbers popping up in spin glasses, popping up in the human brain.
Yeah.
Where else are they?
So the applications don't stop there. This paper also mentions their use in data mining and cryptography.
Data mining and cryptography. Okay, now I'm really lost. How do P-Adic numbers connect to those fields?
So think about how data is often organized.
Okay.
You have these massive data sets with points that cluster together based on similarities.
Okay, yeah.
And P-Adic numbers can be used for something called hierarchical clustering,
Okay.
which is a way of grouping data points based on their relationships.
So it's that same idea of hierarchy and relationships,
Exactly.
but applied to organizing information.
Exactly.
I can see how that would be useful in data mining.
Right.
But cryptography, That's a completely different animal.
It is, but at its core, cryptography relies on complex mathematical structures to encrypt and decrypt information.
Right.
And it turns out that P-Adic dynamical systems, which are basically sequences of P-Adic numbers generated by certain rules, have properties that make them suitable for cryptographic applications.
So the same number system that might be describing the universe and our brains could also be protecting our online secrets.
It's pretty incredible, isn't it?
Yeah. It is.
Whoa, wait, there's more.
Okay.
This paper even touches on using P-Adic numbers to model fluid flow in geological structures.
Okay, you've lost me. How do numbers relate to the flow of, like, oil or water underground?
So those geological structures often have a hierarchical nature. Think about the branching patterns of capillaries or the intricate networks of fractures in rock formations.
I can see the patterns, but how do P-Adic numbers come in?
Well, remember, P-Adic numbers are all about representing relationships in hierarchy based on divisibility, so they can be used to model the way fluids flow through these complex branching networks.
Wow. Seems like P-Adic numbers are everywhere.
They are.
We started with abstract math, and now we're talking about the human brain, the Earth itself, even the secrets hidden in our data.
Yeah.
It's like they hold a hidden key to understanding the world on multiple levels.
It's really mind-boggling how these numbers, which seem so strange at first, have turned out to have such diverse and unexpected applications.
Yeah.
It really makes you wonder what other hidden connections are still out there waiting to be discovered.
It's a reminder that there's always more to learn, and that the most abstract concepts can sometimes lead to the most practical applications.
Absolutely.
I can't wait to see what else we uncover in the final part of our P-Adic dive. It feels like we've been on this incredible journey, you know?
It has been a journey.
Through this world of P-Adic numbers.
Yeah.
And we've seen how they challenge our usual ideas about size and distance, how they connect to string theory in the human brain.
Yes.
Even how they might be used in fields like data mining and cryptography.
Right.
My mind is still kind of spinning from all this.
It's a lot to take in.
Yeah. But there's one last piece of the puzzle I think that we haven't really explored yet.
Okay.
We've talked a lot about P-Adic integers.
Yes.
But what about P-Adic numbers more generally?
That's a great point, and it's a natural next step in our exploration.
Yeah, so what's the difference?
Right.
Is it like how we have integers and then we have fractions and decimals in our regular number system?
You're exactly right.
Okay.
Remember in part 1 when we talked about how trying to do division in the P-Adic world with base 10 caused problems?
Yeah, that's why we had to use prime numbers for our base.
Precisely. And just like we can extend our familiar integers to include fractions by using negative powers of 10, we can extend P-Adic integers to include negative powers of our prime p.
Okay.
And this gives us the full set of P-Adic numbers.
So a P-Adic number can be like a P-Adic integer plus a fraction where the denominator is a power of p.
Exactly.
Okay.
And this inclusion of negative powers of p allows for a much richer and more complete number system.
Okay, I'm following so far. But what can we actually do with these more general P-Adic numbers then?
Right. So one of the papers mentions an interesting example.
Okay.
It talks about the P-Adic analog of the exponential function.
Hold on, the exponential function.
Yeah.
That's like one of the most important functions in math and science.
Absolutely. It is. And it unlocks all sorts of new possibilities within the P-Adic realm.
So P-Adic numbers let us mirror the familiar concepts of our normal number system. But in this completely different, almost alien way.
I love that analogy.
Yeah.
It's like we're looking at the world through a different lens.
It is.
And this different perspective, this alien perspective, as you call it, is exactly what makes P-Adic numbers so powerful.
It is mind-blowing.
It is.
But why should we as non-mathematicians care about any of this?
That's a great question.
What's the big takeaway here?
The biggest takeaway, I think, is that P-Adic numbers challenge our assumptions about what numbers are and what they can do. And show us that there are other ways of looking at the world, hidden structures we might never have imagined.
It's like realizing that the map we've been using our whole lives isn't the only map out there.
Exactly. And sometimes using a different map can reveal paths and connections we never would have seen otherwise.
Right. Who would have thought that a number system based on divisibility by prime numbers could help us model the human brain?
Yeah.
Or the flow of oil underground?
It's amazing.
It's really incredible.
Yeah.
Well, I think it's time for us to surface from this P-Adic deep dive.
Okay.
But before we go, I want to leave our listeners with something to ponder.
Right.
If a simple shift in perspective, a new way of looking at numbers, can lead to such profound insights, What other hidden structures might be lurking out there, just waiting to be discovered?
That's a great question and a great thought to leave everyone with.
So until next time, keep exploring, keep questioning, and keep diving deep.